Now that we've discussed photoelectric sensors, let's move on to the next set of sensors, and that is inductive and capacitive sensors. Inductive proximity sensors are sensors that will only sense metal. They'll only sense anything that has metal in it. The distance that you have to get from the nose of the sensor, this right here would be the nose of the sensor, is rated and specified in millimeters. So yes, you do have to get fairly close to the sensor for it to work. The smaller the sensors, most inductive sensors have round, are round in nature, so they're round. They vary in sizes. The smaller the sensor diameter, the closer to this target, or the closer the target has to get to the sensor in order for the inductive sensor to sense. Naturally, the larger the sensor, the further away we can be from the sensor itself. Operationally, the sensor consists of a coil, and that's depicted right here. These dots are the wires coming around the coil. It has a high frequency oscillator, and an oscillator is nothing more than something that either produces a sine wave or a square wave. It has a detector circuit, and it has a solid state output switch circuit. Inductive proximity sensors are solid state devices. They have absolutely no moving parts in them. Operationally, this high frequency oscillator is mounted such that it is creating a high frequency field or electromagnetic field type item coming out of this sensor. That's what these lines are shown here. These lines that I've drawn here represent a field coming out of the front of the sensor. When a metal object, and here's this target, when this target enters the high frequency field, this thing called eddy currents are induced into the surface of the object. If you look up eddy currents on the internet, let's take a look at this target. Let's say this target was just a rectangular piece of some sort of metallic material. Eddy currents will tend to go in spirals on the surface of the target. Those eddy currents will cause a loss in the energy that this high frequency oscillator is generating. So as this target gets closer, these eddy currents form on the surface of the item you're sensing. It produces a loss in energy, and the detector circuit can detect that reduction in amplitude, or the loss of energy. And when it detects the loss of energy, that loss can then trigger the output switch, which then closes the solid state switch and tells the sensor and you that there is an object close by. Sensors also come in shielded and non-shielded versions. A shielded sensor will have usually a metal band all the way up to the tip of the nose here. Inside of this, there'll also be what's called a mu metal band. Mu metal is a very soft iron, very conductive to electromagnetic fields, to shield the sensor. And what it's going to do is it's going to direct the electromagnetic fields more out toward the front of the sensor. Non-shielded sensors do not have that shield wrapped around them. Therefore, what happens is the electromagnetic fields are still produced but they also tend to come out of the sides of these sensors. So they're more widely dispersed across the nose of that sensor. So shielded sensors can safely be mounted in a metal panel. Think about mounting a sensor, an inductive sensor in particular. If you're going to mount it in a metal panel or on a metal frame, these sensors detect metal. So if I'm going to have a piece of metal here, and I'm going to mount this sensor in to that piece of metal, if I don't have a shielded sensor, the magnetic field that's being generated out of this sensor could very well sense the material that I have the sensor mounted in. That's not good at all. So a shielded sensor will allow you to mount the sensor in a metal panel or in a metal bracket. When you're mounting inductive proxies next to each other, whether they're shielded or unshielded, you should always leave 2 diameters center to center between the sensors. So here's 2 sensors that are mounted next to each other. Notice here's the center of this, and these are 2 diameters next to each other. Because if you have them closer, that magnetic field being generated can interfere with each other, and the sensor may see each other. Same when you're mounting them face to face or nose to nose. You want 2 sensor diameter distance between the 2 noses so that there's no interference between the 2 sensors. So again, the nominal sensing range of different sensors is a function of the diameter of the sensing area of the sensing coil. The shape of the target and the alloy, by the way, this word should not be allow, it should be alloy, of the sensor also has an effect on the operating range. You'll see over here I have copper targets. One is 3.6 millimeters away, one is 12 millimeters away. Different types of materials have correction factors to correct the distance from the sensor that the object actually has to get. This table shows you some of the multiplying factors. So if I have an inductive prox sensor and I'm trying to sense aluminum foil, the multiplier for a shielded and a non-shielded sensor is 1 to 1. So what that tells me is that if I have a 10 millimeter sensor and I want to sense aluminum foil, 10 millimeters is the distance. So 10 millimeter times 1 is 10 millimeters. If I want to sense stainless steel, and stainless steel is going to depend upon the alloy, the multiplying factor can be anything between 0.35 to 0.65. So think about if I have a 10 millimeter sensor, I have to multiply this by 0.35 or 0.65 or 0.45, something which naturally reduces the sensing distance. I have to get closer to the sensor in order for it to sense that material. For a non-shielded, notice I can get a little bit further away. Remember, non-shielded, I've got a more dispersed magnetic field. Brass is 0.4 on a shielded, 0.55 on non-shielded. Aluminum massive, in other words, a massive block of aluminum. For a shielded sensor, 0.3, very difficult material to sense, by the way. 0.55, non-shielded. You might want to say, what's the difference between aluminum foil and a massive block of aluminum? Well, that term alloy comes up again. It's the molecular structure. It's how it's composed of the different materials. And copper is actually the hardest metal to sense. Here on a shielded sensor, the multiplying factor is 0.25. So on a 10 millimeter sensor, I have to actually get to 2.5 millimeters for it to sense copper. And on a non-shielded, I can get a little bit further away from it than with the shielded sensor. So be aware that if you're replacing a sensor, to either replace it with the exact same type, or be aware of the type of material that it's sensing, so that you don't have problems where the sensor won't sense because the object's not getting close enough to it. All sensors, in particular the inductive proxes, have something called hysteresis. And hysteresis is the distance between the operating points of a sensor, in this case the inductive prox sensor, so that as the target approaches the face of the sensor, it has to get closer to the sensor in order for the sensor to turn on. As the target's moving away from the sensor, it can move further away from the sensor before it turns off. So over here there's a graphic that's depicting this. Here I have what's called an axial approach. The target's coming in this direction. That's this red item. These are the magnetic lines of force. Notice how the sensor has to get in to this point right here before the sensor turns on. But moving away from the item or from the sensor, once it's on, it will stay on out to, let's say, this point right here. So that's hysteresis. You have to get closer to the sensor to turn it on, but as you're moving away, it'll stay on for a longer distance. That also works when you're on what's called a radial approach to the sensor. If you take a look, this target that's moving into this field in this direction has to get into this point before the sensor turns on. However, when it's coming back, it'll stay on until it gets out to this point. So it's called hysteresis. You need to be aware of it. It's not a real big problem, but it could present some difficulties. That's really all there is for inductive proxies. There's rarely any adjustments on them. There's rarely anything that goes wrong other than catastrophic failure with them or being broken by something hitting them. Capacitive sensors are the next group. A capacitive sensor will sense anything that gets within its range. It'll sense paper, wood, metal, liquids, powder, anything that gets in its way or in front of it, it will sense. This is also one of the few sensors that are approved by the Food and Drug Administration, the FDA, to come in direct contact with people and animal consumable food products. Anybody who is working in the food manufacturing business knows that sanitation is a big issue. We need to keep everything clean and safe. And nothing from our process can usually come in contact with those goods or with those products. This is one sensor that has been approved by the FDA, and it can come in direct contact with the foods and products that we consume. The sensor is basically it's a capacitor, not basically, it is a capacitor that has an opened plate on it. If you think about a capacitor, when you learned capacitors, we know that a capacitor is two plates with a dielectric in between. In between this. In our case, the dielectric is going to be air. So our dielectric is going to be air. So here's my target. Here's the front of the sensor. and my dielectric in this case is going to be air. So think about this capacitor as being a device, a capacitor, with one of the plates missing. And what happens is that as a target approaches this plate, and here's that plate, as the target approaches that plate, the capacitance will start to increase. And as the capacitance increases, this oscillator, and here's another oscillator, will increase in amplitude. In the inductive procs, it looked at a reduction in amplitude. In the capacitive sensor, because the capacitance is getting larger, the oscillator amplitude is getting larger. That increase in amplitude is then detected by the detector circuit and will turn on an output, a solid state output switch. Some capacitors have a compensation adjustment. You can see inside this capacitor there are some electrodes. They call these electrodes. You really cannot see them from when looking at the capacitor itself, or at the sensor itself. However, if you think about a capacitive sensor, it can sense anything that gets close to it. And when you're in manufacturing, sometimes the temperature and the environment in the manufacturing floor tracks the outside world. You could get temperature variations such that condensation builds up. The water droplets on the nose of the sensor can actually have the sensor trip and sense that there's something in the way, because it's sensing the water droplets on the top of the sensor. It'll also sense any dust in the air. It'll sense humidity in the air when the humidity gets too high. So there is an adjustment on these sensors to compensate for that. The adjustment can be made to literally see through objects. So you could see through an object to another object. One of the examples, and let me go back here, one of the examples I like to use is at Crayola. Crayola makes crayons and markers. And at Crayola, if you look at a felt tip marker, and this drawing is going to be pretty crude, here's the plastic barrel of it. Inside the marker you have the felt, and there's actually a little ring in here of plastic, and this pen is filled up with ink. Well, they use and there's a cap on this then. So we put the cap on there. They use a capacitive sensor looking at this part of the marker. And they have the compensation adjusted such that it does not see the cap, it does not see the plastic barrel, it does not see the plastic ring, and it doesn't see the felt. So when a dry marker comes through, this sensor will say there's nothing there. However, when there's ink in this marker, the compensation is set up such that it will say, oh, there's something there. So all it's doing is it's looking to see if there's ink in that marker. Very reliable sensing. They also mount one down at the bottom, because if you think about this marker, I don't want ink just at the tip. I want the whole thing filled with ink. But again, the compensation is adjusted such that all it sees is ink. So if the marker has ink in it, the sensor will tell you there's a marker there. If there's no ink in it, it says there's no marker present, and it becomes a reject. Inductive and capacitive sensors are wired exactly like photoelectric sensors. They come in sink or source. They can be normally opened or normally closed. They come in 2, 3, and 4 wire configurations. They come in DC or AC voltage, but primarily DC. And they come in a variety of all types of physical sizes and shape configurations. So in the next series of labs, we're going to deal more with the various different types of sensors and the various different types of wiring configurations of these sensors. So I hope this was helpful, and I'll see you in lab.